Okay, we're going to talk about electric fields now. Okay. Again, this is pretty much all just review at this point. We haven't really done anything too new. Okay. Um, okay. The uh, the symbol and units for electric field. The symbol is just E with an arrow over it because it's a vector. Okay. The units are newtons per coulomb. Okay. Um, or you can also use volts per meter. Okay. Volts per meter. Okay. Um, the equation that relates electric field and electric force is F sub E equals QE. Okay, that's simply the charge in the electric field. Okay, Q is the charge, E is the E field. Okay, okay, E field that the charge is in. E field that charge is in. Okay, so if there's multiple E fields, then you would obviously take the one that the charge is in. Okay, um, and it's important to note too that if Q is a positive charge, okay, then F sub E is in same direction as E field. Okay. So if the charge is positive, then the electric force points in the same direction as the E field. If the charge is if Q is negative, okay, then F sub E opposes E field. Okay, so just keep in mind, negative charges oppose the E field, positive charges go with the E field, right? Okay. A basic equation for the electric field created by a single charge. This is just E equals K Q over R. Okay. And it's similar to the equation that we derived in the gravitation unit, G equals capital G, capital M over R squared, or R squared. Okay. So it's very similar to that equation, right? I mean, you can see the similarities right there. Oh, sorry, this should be R squared down here. Okay. Okay. Now, inside of a conductor, when we're talking electrostatics, inside of a conductor, we have no electric field. Okay. And what's going to happen is because so if this is, for example, a conductor, okay, this is like a block of metal, right? We can say, suppose an external E field is established around a block of metal, okay? Then what's going to happen is the positive charges, if we say it's going down, okay, the positive charges drift down, okay, the negative charges drift up. Drift up, okay, and then those charges create, so the charges create opposing E fields. E fields, okay, that cancel the external E field. Okay. So you'll notice that if you have this block of metal right here, you'll notice that you'll end up with all the positive charges on the bottom. Okay. And then you'll end up with all the negative charges on the top. And when you have those charges, they end up producing a electric field that cancels out the one. So if you see, electric field always goes from positive to negative. So the electric field would go, okay. You see how that works? It would go all, well, it would obviously go all the way. I just didn't draw the arrows all the way, okay? So you would see the electric field goes up that way, and it cancels out the E fields from the external E fields, right? Okay. That's why there's no E field inside of a conductor. This is a kind of a particular case that you can see that might be asked on like an AP exam or on your exams or stuff like that, where you have these two spheres with opposite charges that are set in an E field, and what actually happens is this ends up. You set it kind of off at like an angle. You kind of set it askew, and what will happen is the E field will have different effects on each of these charges. The E field will have different effects on each of the charges, right? What I would say, so the first thing it's going to ask us is to find the moment of inertia, which you don't actually have to do any electrostatics to solve for. That's all mechanics right there. I would do I'm treating both of these as point masses, okay? So that means that the moment of inertia of one of the spheres is just m, and then the distance from the center of mass. This is length 2L, so it's just going to be L, mL squared, okay, for each individual sphere. So I'm doing mL squared plus mL squared equals 2mL squared, okay? Because this is the left, this is the right, okay? And then we're going to say that the rod, it doesn't tell us that the rod has negligible mass, but it doesn't give us the mass of the rod, so we're going to assume it's 0 and has no effect on anything. So the total moment of inertia is just 2mL squared, okay? That's the total moment of inertia right there, okay? To find the net torque on the system, okay, all I would have to do is I remember that net torque is equal to RF sine theta, okay? And so I also need to remember that, the net torque is equal to, the torques that go, clockwise minus the torques that go counterclockwise. That go counterclockwise, right? Or counterclockwise torques minus clockwise torques, okay? If I draw my forces on here, you're going to notice that this force right here, the negative Q, is going to go against the E field, okay? So that's going to be QE, okay? And then the positive sphere is going to go with the E field. That's also going to be QE, okay? Okay, so you have these two opposing forces, right? And these forces, because they are actually not directed, they're not directed directly towards the axis, so it would actually apply some torque on here. And because you'll notice that the two forces, you have your left forces equal your right forces, this is going to end up so this doesn't move at all about its center of mass. And then on top of that, it's going to rotate. Okay, so I need to figure out the clockwise torques minus the counterclockwise torques, okay? Well, that's just going to be, let's see, that's just going to be the distance, r, from the center of mass. That's just going to be L, okay? This right here is my r, which is equal to L, okay? So that's going to be L times the force. The force is QE, L QE, okay? Sine theta, okay? And then it's not just one torque, that's just one torque doing it. These are actually both, by the way, these are both actually working together, okay? These are going to cause the system to rotate this way, okay? Which is going to be counterclockwise, right? Okay, it causes it to rotate counterclockwise. So these are both going to work together, okay? So it's actually going to be that plus another LQE sine theta. Okay? And then that ends up being, the torque ends up being 2 LQE sine theta. Now here's something that's important to note. I actually do need to throw on a negative here. Okay, why am I throwing on on this negative right here? Okay, it's because the torque is a restoring force. Okay, so it's like spring force in an oscillation. It's a restoring force. So what's going to happen is when the dipole rotates, horizontal, and then when it rotates past, the torque is now going to act opposite the motion to bring it back to the center. It's trying to get this to be completely horizontal, but it's going to keep oscillating, right? If the angle theta is sufficiently small, then the dipole oscillates with simple harmonic motion when released from rest. Determine the period of these oscillations. So this is very similar to what we did last unit. Okay, you know that the net torque is equal to I alpha. Okay, and I already figured out earlier that 2. This is my torque right here, right? So I can do negative 2 LQE sine theta, okay, equals I alpha, okay? And I can make my substitutions. I can substitute I. I already know what I is from up here, okay, 2 ml squared. Okay, so then this becomes negative 2 LQE sine theta equals 2 ml squared times alpha. Okay. I don't know what alpha is. Okay, but I'll tell you what, it's not really going to matter what alpha is. Okay. Again, also, it says that small angle approximation is in play here, so sine theta becomes theta. Okay. So this is really just negative 2 LQE theta equals 2 ml squared alpha. Okay. Now, there are a couple things that can cancel out here. I can cancel out a 2 on both sides. I can cancel out one of my L's. Okay. Is there anything else I can cancel out here? It doesn't look like I can cancel anything else out. So it ends up being QE theta, negative QE theta. Okay. If I divide both sides by ml to get the alpha on one side, this ends up becoming negative QE over ml theta equals alpha. And this right here is the simple harmonic motion differential equation, right? This part right here is going to be my negative omega squared, okay? If I drop the negative, then I'll see that, let me get a different color and go off to the side here, okay? If I drop the negative, then it ends up being omega squared is equal to QE over ml, okay? And then I root both sides, okay? This becomes omega equals root QE over ml. And then I replace omega with 2 pi over t. 2 pi over t equals root QE over ml, okay? And then I flip both sides and multiply by 2 pi, and I should end up getting t equals 2 pi root ml over QE. Okay, you see how that works out? Okay, so that's going to be the period of the oscillations. Okay, all right, that is section 3.